All right, so angular speed and velocity are just like speed and velocity in a linear sense, except now we're going to travel around a circular path. And since we're traveling around a circular path, since we're traveling along an arc, the arc is the length. And that arc has a relationship to the radius of the circle and to the angle of the circle. So we can define the average and instantaneous angular speed by this. This is like the average, okay? Angular speed. And what that is, that's just delta theta over delta time. How much of an angle do we change over time? How much do we rotate around the circle over time? And that rotation is measured by the angle over time. Now, instantaneous is right then and there. If I could take a snapshot in time, what would that look like? Now, if we rearrange this relationship, we can also solve for the angle theta if we know the angular speed. So this is going to be the angular speed. Okay? Now, a lot of students call that W. It's a Greek letter. I don't know. I've been teaching a while. I just say, oh, yeah, the W, the funny curly W. Just know that that symbol means angular speed in physics. Okay? Any questions on that? So those are the two formulas you'll use for your homework. And so angular speed and velocity, we have this thing that we call the right-hand rule. So the direction of the angular velocity is along the axis of rotation that is given by what we call the right-hand rule. Everybody take out your right hand and hold it in the air and wave it like you just don't care. I've always wanted to do that. All right, now, when think of this, your thumb always points in that angular velocity if you curl your hand around like it's a wheel. So if you pretend your hand is the wheel, that is all. You have to. That's why it's called the right-hand rule. It won't work with the left hand. All right, and this is based on vector mathematics. We won't go into all the details today. But if you have a wheel that's rotating forward, which way will that angular velocity point? The way that your left thumb does. So because this wheel is rotating this way, if I take my right hand and I rotate in that same direction, then the angular velocity is pointing away from the wheel. And it's perpendicular to the wheel, perpendicular to the rotation of the circular object. Now, if I'm rotating this way, if the wheel's rotating the other way, you still use your right hand, but notice where my thumb goes? So if my wheel is rotating this way, my thumb still points. Does that make sense? And that's why that wheel, that video we just saw, that demonstration, that's why the wheel was kind of floating. Part of the reason. It had to do with the way in which he was rotating the wheel, the direction that he was rotating the wheel. Does that make sense? Okay. Any questions on that? Does everybody have this drawn? Now what's funny is every time I teach this, when I give the test, I know when people get to these right-hand rule questions, because y'all look out and they'll have their pencils in their hand, they'll set their pencil. And they write it down. Okay? So that's very helpful. Okay? So, angular speed and velocity speed, there's a relationship between the tangential, right? Tangent means that it's a 90-degree angle to the radius. So right here, we've got a 90-degree angle to the radius. Tangential also means that it intersects the circle only one time. Okay? It intersects the circle only one time. It intersects the circle only one time. So remember the hammer thrower? He's spinning the hammer around, he's spinning it around, spins it around. As soon as he lets go, that ball will follow the tangential path. But the velocity remains the same. In other words, if he's spinning around at 30 meters per second, the speed is 30 meters per second, and it follows the circular path, but the instant he lets go, it follows the straight path. So, the tangential is always going to be the straight path. And Newton said that's what objects prefer to travel in, right, is the straight path. And then the angular speeds are when it's on the curve. And so the angular speed or velocity is just going to be the radius of the circle times the angular what was I trying to say? Oh, the velocity, yeah, the tangential, that's the relationship between the angular speed and the tangential speed. So here we have a tangential speed, right? And that is going to be equal to the radius of the circle times the angular speed. In other words, how fast does this spin times that radius, r. And so what does that mean? That means that the parts of the rotating object further from the axis of rotation move faster. This is how gears work, right? If I take a really big gear and the further I go out, in other words, like a planet that's very, very far out, has a very far orbit, although orbits of planets are elliptical, more so than circular, but let's assume they're circular. Those are traveling much faster. This path here is much smaller because it's closer, because its radius is shorter. And since mathematically that the tangential velocity is equal to the radius times the angular speed, notice that this vector is shorter than this vector. And that has to do with the relationship between the circumference of the circle. It's literally traveling a longer distance. See, if I take this circular track and I leave this on here and I rotate this around, whoops, and I rotate this around and I pretty much leave my hand the same, this has a certain tangential speed because of the radius of the path that it travels. Now, if it were possible and I could put a bigger circle, when this makes a rotation, this object that's way out here has to travel a further distance in the same amount of time. Because really, in both cases, we're taking the circle, the distance, the arc length, is much larger on a larger circle, right? Do you guys see that? The larger circle has the larger circumference, but the same amount of time, right? So if I take this car and I go 1/2 a turn in 1 second, well, it's only traveling 1/2 of this length. But if I take a circle that's twice the size of this, or it has twice the radius of this, well, then the length would be longer too. And it wouldn't matter. It would still have to travel twice as long in the same time. That's what this is saying. We'll do some labs with that. Any questions on that? So the period is the time that it takes for one rotation, and the frequency is the number of rotations per second. So the period t, we always represent that by a capital T, and the frequency f has a mathematical relationship. And the relation of the frequency to the angular speed is this right here. And that's it. I mean, I don't want to over-explain it. It's pretty simple. The period is the time that it takes for one rotation. So what we're concerned with is how long does it take for an object to take one full rotation of the circle? We call that a period. The reason we call it a period is because it's periodic behavior. at some point the behavior just repeats itself, right? So technically when we talk about circular motion, we're only concerned with one rotation. After that, the information just gets repeated, right? So if I were to measure the distance of this, because it's a closed path, the distance that this travels from here to here is one full period. One rotation around the circle is one full period. If I rotate it twice, well, whatever the original distance is, the arc length, is now twice that. So it's periodic behavior. It's the same distance every time. We could just multiply it by 2 or multiply it by 3, depending on how many rotations it is. Now the frequency is the time it takes, or how many rotations it can fit in 1 second. So if this is going really, really fast, I can measure that. And then the relationship, we said that the angular speed had a relationship too. And so if we take those previous equations that you've written down and we substitute a few things in, we'll get the relationship between the angular speed is 2 pi over t. And then remember that 1 over t is f. So if we replace this 1 over t with f, we get 2 pi f. Does that make sense?